Welcome back to this video tutorial. In this video we will discuss about different mechanism for synchronizing data transfer between the processor and memory. In the previous video we have discussed one such mechanism, that was program controlled I/O, in which the processor continuously monitors the status of the device. Okay, the processor wants to continuously monitors the status of the device in order to identify whenever the device become ready for I/O data transfer. So that technique, that disadvantage of that technique was does not perform any useful task during that monitoring. Okay, so here we have introduced a new technique based on interrupt. In interrupt mechanism, this is an alternative approach and would be for the I/O devices to alter the processor when it become ready. Here the device itself inform the processor that the device is ready for I/O, device is ready for data transfer, and it do so by sending a hardware signal called interrupt to the processor. Okay, the device use a special hardware signal called the interrupt to inform the processor that the device is ready for data transfer. At least one of the bus control lines called an interrupt request line is dedicated for this purpose. A special control line called an interrupt request line is used for this purpose. Processor can perform other useful tasks while it is waiting for the devices to be ready. This is the advantage of this interrupt based mechanism, in which processor can perform some useful tasks while it is waiting for a device to be ready. If the device become ready, it automatically send an interrupt signal to the processor to indicate that the device is ready for data transfer. Okay, so consider this one example, and this processor is executing an instruction located at address I when an interrupt occurs. That is, processor is currently executing program 1. While executing the ith instruction of program 1, an interrupt occurs. Okay, so that the processor want to suspend the execution of program 1 and want to execute the interrupt service routine corresponding to this interrupt request. The routine executed in response to an interrupt request is called the interrupt service routine. The service want to perform in order to satisfy the interrupt request is known as interrupt service routine. When an interrupt occurs, control must be transferred to the interrupt service routine. Okay, so after completing the ith instructions execution, processor want to transfer the control to the starting of this interrupt service routine. So before transferring the control to this interrupt service routine, the processor store the content of program counter. Now the program counter holds the address of I plus 1th instruction of program 1. So processor want to store the address or the content of program counter onto the processor stack in order to return back to that location after completing the interrupt service routine execution, so that it can properly resume the execution of this suspended program 1 execution from this I plus 1th instruction onwards. Okay, the treatment of an interrupt service routine is very similar to that of a subroutine. The working principle of interrupt service routine is similar to that of a subroutine execution, but there are some difference. That is, a subroutine perform a task that is required by the calling program itself. The calling program is a program that calls a subroutine, and subroutine perform a certain task. So usually is a part or perform the subroutine perform certain task in order to support the execution of the calling program. But in case of interrupt service routine, it may not have anything in common with the program it interrupt. That means the interrupt service routine performs certain task that may not have any connection with the program that is suspended by servicing such interrupt request. Okay, interrupt service routine and program that it interrupt may belong to different users. One more difference, sometimes the interrupt service routine and the program that it interrupt or that suspended by the interrupt request may belong to different users. Okay, as a result, before branching to the interrupt service routine, the processor want to store the program counter content and information, other information such as condition code flags and processor register, etc., and are stored on the stack top. Okay, this will enable the interrupted program to resume execution upon return from the interrupt service routine. If we store all these types of information properly on the top of the processor stack, so that after completing the interrupt service routine execution, we can return back to the suspended program so that it can properly execute the or resume the execution of the program 1 from the suspended location onwards. Okay. Saving and restoring information can be done automatically by the processor or explicitly by program instructions. So, processor automatically perform storing operation as well as retrieving operations. Also, we can use program instruction in order to perform such operations. Saving and restoring registers involve memory transfers. It increases the total execution time. Increases the delay between the time an interrupt request is received and the start of execution of the interrupt service routine, and this delay is called interrupt latency. So, before starting the execution or before starting the service of an interrupt service routine, we want to store a large amount of data, and the storing of this much of information actually require many memory reference operations. Okay, and these memory reference operation takes a large amount of execution time, and it increases interrupt latency. What is this interrupt latency? This interrupt latency means the time interval between the arrival of an interrupt request and the start of the execution of interrupt service routine. Time interval between arrival of interrupt request and the start of execution of the interrupt service routine. If we want to store large amount of data before starting the execution, it takes large amount of execution time, so that it increases the interrupt latency. In order to reduce the interrupt latency, most processors save only minimal amount of information like program counter value and processor status register information. Okay, so we want to reduce the interrupt latency. What is the mechanism we use to reduce the interrupt latency? Before starting the execution, after arriving the interrupt request, we can store a minimum amount of information before starting the execution of the interrupt service routine, so that we can reduce the interrupt latency. So the minimum amount of information that we want to store before starting the execution include program counter information and the processor status register information. Any additional information that must be saved and must be saved explicitly by the program instruction at the beginning of the interrupt service routine, just like the subroutine execution. This is example that we have already discussed in the topic subroutine execution. Here, after calling the subroutine and start the execution of subroutine body, at the beginning of this subroutine body we have a special instruction. This instruction is for storing the content of register R0, R1 and R2 onto the stack top. Okay, why we want to store this register information onto stack? Because these set of register are used commonly by this calling program and the subroutine. Okay, similarly, while calling or starting the execution of an interrupt service routine, at the start of this interrupt service routine we have such instruction in order to store register content onto the stack of the processor stack, so that the register set, which are common for both the suspended program, interrupted program, as well as inside the body of the interrupt service routine, so that we can use the register set inside the interrupt service routine without causing any problem to the interrupter, without losing any data. Sorry. without losing sorry, without losing any data associated with the interrupted program. Okay, so we need, or we can attach certain instruction at the beginning of the interrupt service routine in order to store the common data between the interrupted program and the interrupt service routine. Any additional information that must be saved at the beginning by using a separate set of instruction at the beginning of the interrupt service routine, using separate set of instruction just like this. Okay. Another approach in order to reduce the interrupt latency is use duplicate set of processor register by the interrupt service routine. Another technique for reducing the interrupt latency is inside the interrupt service routine body, use separate duplicate set of register. But the problem is we need large number of register in such mechanism. Okay. When a processor receives an interrupt request, it must branch to interrupt service routine. It must also inform the device that it has recognized the interrupt. So, whenever a processor receives an interrupt request, if it is ready to accept the request, it starts the execution of the interrupt service routine. One more thing the processor wants to do is inform the requested device that its request has been recognized by the processor and going to execute next. Okay, so the processor need a mechanism to inform the device about this recognition. Okay, we have two mechanisms, that is, some processor have an explicit interrupt acknowledgement control signal for this purpose. Some processor use interrupt acknowledgement mechanism, that is, whenever a processor ready to accept an interrupt request, then after recognizing the interrupt request, the processor send a special acknowledgement signal back to the device indicating that the processor accepts its interrupt request and going to execute next. Okay. In other case, the data transfer takes place between the device and the processor can be used to inform the device. That is, whenever a data transfer starts between the processor and the device understands that its interrupt request is accepted by the processor. That is why this data transfer taking place now. Okay. Next is about enabling and disabling interrupts. That is, enabling and disabling interrupt requests. Okay. Interrupt can be arrived at any time. They may alter the sequence of event to be performed. Hence, the interruption of a program execution must be carefully controlled. That is, we have a system in which different types of I/O devices, memory, processor, all are connected through an interconnection bus system. Okay, in which different devices are associated so that devices can send interrupt requests at any time without considering the activities of other devices. That is, different devices can place interrupt at any devices. So, we need separate mechanism for enabling and disabling these interrupt requests. Okay. Consider some situation in which the processor is generating certain set of output data that want to print using a printer unit. Okay. So, an interrupt request from the printer should be accepted only if there are output line to be printed. After printing the last line of a set of n lines, the interrupt should be disabled until another set become available for printing. That is, the processor is generating certain resultant values that want to print using a printer unit. Okay, so processor is continuously generating different values, and processor interrupt the processor indicate or inform the processor that it become ready for printing next value by sending interrupt request. Okay, whenever the data generated by the processor is completely printed by the printer, and after printer become ready to, or printer become free, printer again send an interrupt signal to indicate that it become ready to accept new set of data for printing. But now the situation is the entire resultant value which are generated by the processor is already consumed by this printer unit. So that now we have no data for printing. Okay, so in that cases the processor want to block the further interrupt request from the printing unit, and also want to enable the request from the printer unit after getting new resultant value for printing. Okay, so in certain situation the processor want to enable new interrupt request, and some other situation processor want to disable further interrupt request. So here we have a mechanism, that is using a machine instruction in order to enable and disable interrupt request. They are interrupt enable and interrupt disable instructions. Interrupt enable instruction and interrupt disable machine instruction. Okay, that and it's how it works. One bit in the processor status register called an interrupt enable bit indicate whether interrupts are enabled. So for enabling and disabling of interrupt, the processor status register is associated with a special bit of information, call it as the interrupt enable bit. Okay, this value of this particular interrupt enable bit indicate that whenever the processor is ready to accept interrupt, and if the processor is busy with some other interrupt action. Okay, an interrupt request received while this bit is equal to 1 will be accepted. This is the case. The interrupt request received while this bit is equal to 1 will be accepted by the processor and perform the following before starting the execution of interrupt service routine. Okay, after saving the content of processor status register on the stack with the interrupt enable bit equal to 1, the processor clears the interrupt enable bit in its processor status register, thus disabling further interrupts. When a return from the interrupt instruction is executed, the content of the processor status register are restored from the stack, setting the interrupt enable bit back to 1. Hence, interrupts are again enabled. That means whenever a processor is ready to accept a new interrupt service request from some of the IO device, then in such situation processor enable or the enable bit interrupt enable bit of the processor status register is set as 1. The value of interrupt enable bit equal to 1 means processor is ready to accept a new signal, no interrupt signal. Okay, or new interrupt request. Whenever this value equal to 1 and the processor is ready to accept a new request, so that the newly coming interrupt request will be accepted by the processor. Okay, whenever the processor receives a new interrupt request, it stores its processor status register content and return address onto the processor's on this top of the stack, and after that make the value of interrupt enable bit as 0. The interrupt enable bit value as 0 indicates that now the processor is busy with some interrupt service routine, so that it can't accept a new interrupt routine next. So the further requests coming from different IO devices are in a blocked state, because the interrupt enable bits value now is equal to 0. Okay, after completing the current execution of interrupt service routine, the processor want to enable the interrupt enable bits value equal to 1. Okay, what's the meaning of setting interrupt enable bit value equal to 1? The meaning is now the processor complete some task and is ready to accept a new interrupt request. Okay, after completing the current execution of interrupt service routine, the processor perform or get back the processor status register information back to restore the processor status register from the stack and set the interrupt enable bit back to 1. Okay, hence the interrupt enable bit equal to 1 means again the interrupt service is enabled by the processor. Okay. Next is about sequence of steps involved in handling an interrupt request from a single device. Handling, how to handle a sequence of interrupt request from a single device. The device arises an interrupt request. Okay. The processor interrupts the program currently being executed. The further interrupts are disabled by changing the control bit in the processor status register. Initially it is 1, now it is reset to 0. The device is informed that its interrupt request has been recognized, and in response the device deactivates the interrupt request signal. So, for informing the processor use interrupt acknowledgement mechanism. The program counter is loaded with the starting address of the interrupt service routine, and the action requested by the interrupt is performed by the interrupt service routine. The interrupts are enabled, that is set back to 1, and the program counter and the processor status register are stored, and the execution of the interrupt program is resumed. These are the set of activities involved for handling sequence of interrupt from a single device. Notice, this is to handle sequence of interrupt request from a single device. What are the steps? First, the device generate an interrupt request. Okay, if the processor is ready to accept the request, the processor if the processor is ready to accept the newly coming interrupt request, then the processor interrupt the currently executing program, then store the program counter value onto the processor stack, and change the processor interrupt enabled bits value from 1 to 0. That means processor is not ready to accept any interrupt request further. Okay. And after that, the processor want to inform the device that its interrupt request has been recognized and going to service next. In order to perform that, the processor generate an interrupt acknowledgement signal. Okay, after completing the interrupt service routine execution, the processor restore the program counter value and processor status register value from the stack, and make the interrupt enabled bits value or set the interrupt enabled value back to 1. This indicates that now the processor is ready to accept new interrupt requests from various devices. Okay. So and also after setting all this value, after setting this interrupt enabled bit value as 1, and after restoring the program counter value, the processor can resume the execution of the interrupt program from the stop location onwards. Okay. And next is about how to handle interrupt from multiple devices. The previous case is prevent or handling sequence of interrupt requests from a single device. Next is about handling interrupt request from multiple devices connected with the common bus system. Okay, multiple IO devices may be connected to the processor and the memory via bus. Some or all of these devices may be capable of generating interrupt requests. Okay, each device operates independently, and hence no definite order can be imposed on how the devices generate interrupt requests. So this is a complex situation, that is bus is associated with different IO units, memory, processor, etc., and all these units are working independent of each other, so that each device can generate its own interrupt request at any time without interacting with other devices connected with the bus system. So in such situation we have to face different complex situations, like how does the processor know which device has generated an interrupt? How does the processor know which interrupt service routine need to be executed next? When the processor is executing an interrupt service routine for one device, can other device interrupt the processor? If two interrupt requests are received simultaneously, then how to break the tie between them? These are some difficult tasks we have to face in case of handling interrupt from multiple devices. So we need separate mechanism for handling all these situations in order to handle interrupt from multiple devices. Okay, consider this situation or this arrangement. Bus is associated with processor, keyboard and display unit. Okay, how does the processor know which device has generated an interrupt? Okay, here the processor and keyboard display, these units are connected through a common bus, and the processor want to know whenever a processor receives an interrupt request, the processor want to identify which among these units generate that particular interrupt. Okay, so we have a mechanism, that is polling mechanism. In this, polling means we have already learned about this polling mechanism in a section that is about program controlled I/O, in which the processor want to continuously monitor the status bit information. Okay, whenever the status bit unit equal to 1, that means that device is ready to generate ready for data transfer. Okay, but here the status register of each device has an IRQ bit which is set to 1 when it requests an interrupt. Okay, here the status register of this device, the device in IO device interface is associated with a status register, and the status register has an interrupt request bit, a special bit, interrupt request bit. DIRQ means display interrupt request bit, KIRQ means keyboard interrupt request bit. The interrupt service routine can poll the IO devices connected to the bus. Interrupt service routine can poll the IO devices connected to the bus. The first device with IRQ equal to 1 is the one that is serviced next. Okay, so the same working principle of polling mechanism that we have discussed in case of program controlled IO. Here also the polling mechanism works like select the processor want to monitor the value of this IRQ bits of different units associated with this bus interconnection. Okay, and identify which are the devices whose interrupt request value become 1 now, and poll the devices which set the IRQ which set its IRQ bit as 1 first. That means this polling mechanism is based on first come first serve basis. That is, the device which set the IRQ value as 1 first is serviced next. That is the polling mechanism for identifying the device which generate an interrupt request. Okay, once more, the IO interface is associated with the status register, and status register contains a special bit of information in order to indicate whether the device is requesting an interrupt or not. Okay, keyboard is for representing keyboard, we have KIRQ bit, keyboard interrupt request bit, and for supporting the interrupt action of display unit, we have this DIRQ bit here. Okay, if KIRQ bit equal to 1, that means the display unit is already generated an interrupt request. If DIRQ equal to 1, that means the display KIRQ equal to 1 means keyboard unit generate an interrupt request. Okay, if DIRQ equal to 1 means display unit already placed an interrupt request. So, in order to work this polling mechanism, first identify the devices or units which have set its this in IRQ bit as 1. Okay, then identify among them which one set the IRQ bit as 1 first. So, the device which set the IRQ equal to 1 first is serviced next. This is polling mechanism, and is a simple mechanism, and the problem is its activities. This polling mechanism consumes to query the status bits of all the IO devices in order to identify which are the devices set its IRQ bit as 1, and also want to identify which among them set its IRQ bit as 1 first. So it is a time consuming activity. And another mechanism is vectored interrupt mechanism. And the steps involved in this vectored interrupt mechanism are: device sends an interrupt request signal and is represented as INTR, interrupt request signal. Okay, if the processor is ready to accept the interrupt request, it, after completing the current instruction of the program which is going to interrupt due to this interrupt action. Okay, after the processor want to send an interrupt after receiving the interrupt request from a particular device, it generates an interrupt acknowledgement signal by activating the interrupt acknowledgement line. Okay, then device sends the interrupt vector code and turns off the interrupt request. After accepting an interrupt request by the processor generates an interrupt acknowledgement signal in order to indicate that the device is going to execute a particular device interrupt request. Okay, after placing this acknowledgement signal, the device identifies that whose interrupt is going to execute next, so that the device plays a special interrupt vector code. So we can elaborate the working of this third step here. How to send this interrupt vector code? Device can send a special code of length some 4 to 8 bits to the processor over the data bus. Code supplied by the device may represent a part of the starting address of the interrupt service routine. The remainder of the starting address is supplied by the processor based on the area in its memory where the addresses of the interrupt service routines are located. The location pointed to by the interrupting device is used to store the starting address of the interrupt service routine. The processor reads this address and load it into the program counter. Okay, so this is the elaboration of this third step here. The first, after sending an acknowledgement signal, the device which identifies that its interrupt request is going to service next, so that the device next plays a special vector of length 4 to 8 bits. Okay, this is known as interrupt vector code, and this interrupt vector code indicates a part of the starting address of its interrupt service routine, and the remaining part of this interrupt service routine address is provided by the processor itself. After combining these two information, we get the entire address information. So fetch that address information, then store it into a memory location which is pointed by the device itself. Okay, after identifying the starting address of the interrupt service routine by combining two information, combining the address information from the interrupt vector code which is sent by the device who placed the interrupt request, and the remaining part is provided by the processor itself. After combining these two information together, generate the whole starting address of the interrupt service routine, so that the processor want to store this interrupt service routine address to a particular location which is specified by the device who placed that interrupt request. Okay, so after placing that address location to a address of the starting address of the interrupt service routine to a location specified by the device, processor want to store that address into the program counter register. Then only the processor can start the execution, or only the processor can move the control from the interrupted program to the start of the interrupt service routine. Now the processor can start the execution of interrupt service routine. This is an important mechanism, so try to understand well First, the device send an interrupt request, which is willing to get an interrupt service routine from the processor. Okay, after sending an interrupt request, whether the processor is ready to accept the request, it generate an interrupt acknowledgement signal. Okay, whenever the device identifies this interrupt acknowledgement signal, then it identifies that its request is recognized by the processor and going to process next, so that the device want to send a special code of information, call it as vector code, interrupt vector code. So the device next send an interrupt vector code to the processor, which indicate a part of the starting address of the interrupt service routine, which going to execute for its interrupt request, and the remaining part of the interrupt service routine address is provided by or identified by the processor itself. So combining these two information get the exact starting address of the interrupt service routine. Okay, after that the processor want to store this starting address of the interrupt service routine to a location which is specified by the device which generate the interrupt request itself. Okay, and also wants to store the starting address of the interrupt service routine to the program counter for starting the execution of the interrupt service routine. Okay, so this is an important mechanism. Try to understand the steps carefully. Okay, where we use this mechanism is used for handling interrupt requests from multiple devices. Okay, and next is about how to handle nesting of interrupt. That is, when the processor is executing an interrupt service routine for one device, then can other device interrupt the processor? Is it possible for other devices to interrupt the processor current execution of interrupt service routine? If two interrupt requests are received simultaneously, then how to break the tie between these simultaneous requests? These are the situation. Okay, in the previous case, before the processor started executing the interrupt service routine for a device, it disabled the interrupt from the device. How it possible? Whenever the processor start the execution of an interrupt service routine, before starting the execution, processor itself disable the interrupt enable bit. That is, processor disable the interrupt enable bit which is present in the processor status register as 0. That indicates processor is not ready to accept further interrupt request. Okay, in general, some arrangement is used when multiple devices can send interrupt request to the processor. During the execution of an interrupt service routine of device, the processor does not accept interrupt request from any other devices. Since the interrupt service routine are usually short, the delay that this causes is generally acceptable. However, for certain devices, this delay may not be acceptable. That means, in usual cases, we can interrupt or block further interrupt request while the processor is dealing with the interrupt service routine of a particular device. While dealing with the interrupt service routine of a particular device, processor can block further interrupt request before completing the execution. How it possible? The processor set the interrupt enable bits value as 0 before starting the execution of the interrupt service routine of a particular device. This indicates that before completing the execution of that particular interrupt service routine, processor is not ready to accept any further request. This is possible in almost all cases because the time taken to complete the interrupt service routine is very small. So that delay is acceptable in almost all cases. But in certain situation, such small delays is also very such delay may make some problem in certain situations. That means certain types of interrupt request does not support any type of delay. Okay, so in such situation we need separate mechanism for handling interrupt request in such cases. Okay, Which devices can be allowed to interrupt a processor when it is executing an interrupt service routine of another device? Okay, certain situation, processor is currently executing with an interrupt service routine. At that time, certain interrupt request, new interrupt requests arise which are not ready to accept any delay. Okay, certain interrupt requests are not ready to accept any delay. That means they are that much important. Such cases, processor want to perform certain other action in order to handle such situation. What are they? An interrupt request from a high priority device is accepted while the processor is executing the interrupt service routine of a low priority device. That is, certain devices with high priority. The interrupt request from a device with high priority must be given high or fast service. The device with high priority, the request from a high priority device must be get serviced first. So that in that cases, the processor want to suspend the execution of an interrupt service routine from a low priority device in order to service the request from a high priority device. Okay, so this is a priority based mechanism. So we have a note here. A priority level is assigned to the processor that can be changed under program control. Processor's priority is encoded in few bits of the processor status register. It can be changed by program instruction that write into the processor status register. These are privileged instruction which can be executed only when executing operating system routine. That is, processor's priority is always associated with the currently executing program. The processor priority is actually equal to the currently executing program's priority. So the processor priority is always in a changing value. Okay, and also processor priority is always marked or encoded using few bits of information of processor status register. Processor priority is marked inside the processor status register using a few bit of information. So we have certain set of privileged instruction in order to change the processor priority value. Okay, so we use certain privileged set of instruction in order to mark or update the processor priority value with respect to the priority of the currently executing program. Okay, the priority level of the processor is the priority of the program that is currently being executed. Okay, this is an important point. Priority level of a processor. The processor's priority is always in a changing value and its priority is always associated with the priority of the program that is currently being executed. When the processor starts executing the interrupt service routine of a device, its priority is rise to that of the device. If the device sending an interrupt request has a higher priority than the processor accepts the interrupt request. If the device sending an interrupt request which has higher priority than the processor's current priority, then the processor accepts the new interrupt request. That means the processor want to suspend the execution of current interrupt service routine and want to accept the high priority interrupt request. Okay. So here we have a implementation mechanism. Implementation of interrupt priority using individual interrupt request and acknowledgement lines. Individual interrupt request and acknowledgement lines. Okay, each device has a separate interrupt request and interrupt acknowledgement line. Each device has its own interrupt request, okay, and separate acknowledgement lines. The interrupt requests received over these lines are sent to a priority arbitration circuit in the processor. Processor is with a priority arbitration unit and the interrupt requests are mapped to this priority arbitration unit. The interrupt request has higher priority level than the priority of the processor, then the request is accepted. Okay. Processor is now dealing with certain interrupt service routine, and here with this priority arbitration unit we have this processor is accepting different interrupt requests. If any of these interrupt requests has higher priority than the processor's current priority value, then the processor wants to suspend the current execution and start to process or service the higher priority request next. Okay, and next is about simultaneous interrupt request. Simultaneous arrivals of interrupt request from two or more devices. How to handle simultaneous interrupt request arrival from two or more devices? This is using a priority scheme. Solution is straightforward. Okay, the processor is simply accept the request having higher priority. Okay, if we follow this system and different devices have different priority, then we have no complication. If two different devices requesting for a service from the processor, then the higher prior request will be processed first. Okay, if the situation become worse if several devices share one interrupt request line. Okay, here we have separate interrupt request line, so the situation is very simple. We want to consider the priority values of different interrupt requests with respect to the priority of different devices. But the situation is different here. If several devices share one interrupt request line, some other mechanism is needed, and the mechanism are polling scheme. If the processor uses a polling mechanism to poll the status register of I/O devices to determine which device is requesting an interrupt. In this case, the priority is determined by the order in which the devices are polled. The first device with status bit set to 1 is the device whose interrupt request is accepted. When vectored interrupts are used, select only one device to send its interrupt vector code. And widely used scheme is to connect the devices to form a daisy chain. In polling mechanism, the processor wants to understand the status bits information. Okay, IRQ bit information. In this case, identify the devices whose IRQ value equal to 1. That means the devices which are already placed interrupt request. Okay, after identifying the devices which are placed interrupt request, then identify which among them place the interrupt request first. Okay, the first one which set the interrupt request or which send the interrupt request will get the service first. Okay, this is the polling scheme based on first come first serve basis. That means the device which place the interrupt service request first will get the service first. When vectored interrupt are used, select only one device to send its interrupt vector code. Second is based on vectored interrupt mechanism, and select only one device to send its interrupt vector code. And here we use a separate mechanism based on daisy chain. Consider the second mechanism using daisy chain. Here all the devices share a common interrupt request line, and the devices are connected through daisy chain manner, or the acknowledgement lines are connected with the devices in a daisy chain manner. That means processor generate the acknowledgement line with the device 1 only. If the device 1 accepted the acknowledgement from the processor, then it blocked the movement of this acknowledgement to the device 2. If it is not accepted, then it receives the acknowledgement and passed to device 2. If the device 2 accepted the acknowledgement, then it blocked further movement of this acknowledgement from this device 2. If it is not accepting, if it is not willing to accept this acknowledgement, then pass the acknowledgement signal to the next device, and so on. This is the working of daisy chain. Okay, this is the vectored interrupt mechanism based on daisy chain. Okay, in order to handle sequence of simultaneous interrupt requests from different devices. Here devices share an interrupt request line, and interrupt acknowledgement line is connected in the form of daisy chain. Okay, when the device raises an interrupt request, the interrupt request line is activated. That means 1, 2 or 3, any number of devices can activate the interrupt request line at the same time. The processor in response activates an interrupt acknowledgement line, and this interrupt acknowledgement line is directly connected with device 1 only. Okay, if the device 1 is not ready to accept the acknowledgement, then it can receive and pass to the next device. If it is accepting this acknowledgement, then it blocks the movement of acknowledgement to the next device. That is the working. Suppose device 1 is not ready to, or is not willing to send an interrupt request. Device 2 alone, or device 2 alone is ready to want to send an interrupt request. In that case, if the processor is ready to accept the request, after accepting the request, it generates an interrupt acknowledgement. Okay, so after receiving this interrupt acknowledgement signal here in device 1, it checks whether it is acknowledgement is based on its request. Okay, that means if device already placed an interrupt request, then it accepts the interrupt acknowledgement. In our case, device 1 is not willing previously, so it not placed any interrupt request here, so that it just receive other request and pass to the device 2. Okay, and device 2 identify that it already placed an interrupt request in the bus, and so that it accepts the interrupt acknowledgement line. Okay, so its request get processed by the processor next. Similarly, suppose device 2 and device N simultaneously place an interrupt request, and the processor accepts the request, generate an interrupt acknowledgement signal, which is directly moved to the device 1. Device 1 check the acknowledgement and identify that it is not, or device 1 is not already placed any interrupt request, so that it receive and pass that acknowledgement to device 2. Device 2 identifies that it already placed an acknowledgement, now it already placed an interrupt request, now it receives an acknowledgement, so that its request going to process by the processor next. But device N is also placed an request here, but the first device whose request get serviced first here is the request of device 2. Okay, this is the case of daisy chain, so that the priority is based on the physical location. The device which is present near to the processor has higher priority in case of daisy chain mechanism. Once more, the priority, the device that is electrically closest to the processor has the higher priority. Always remember this case in case of daisy chain mechanism. The devices, among the different devices which are placed interrupt request, the device which is physically closest to the processor get the service first from the processor. Okay, when IO devices were recognized into a priority structure, each device had its own interrupt request and interrupt acknowledgement line. The priority based scheme separate interrupt acknowledgement interrupt request line. Okay, when IO devices were organized in a daisy chain fashion, devices shared an interrupt request line like this, and the interrupt acknowledgement propagate through the devices in a daisy chain manner. We have a combination of the priority structure and daisy chain mechanism as like given here. In the priority groups, here we have different priority group. Each of these group is implemented using this daisy chain mechanism, and different group form a priority structure just like this structure. Here we have priority arbitration circuit. So request from different group is connected with the priority arbitration circuit, and this unit select the request in order to service next based on the the priority value of different interrupt. Okay, devices are organized into groups. Each group is assigned a different priority level. All the devices within a single group share an interrupt request line and are connected to the form of a daisy chain. Okay, and next is about controlling device requests. Controlling device request. Okay, only those devices that are being used in a program should be allowed to generate interrupt request. To control which devices are allowed to generate interrupt request, the interface circuit of each I/O devices has an interrupt enabled bit. If the interrupt enabled bit in the device interface is set to 1, then the device is allowed to generate an interrupt request. Okay, those devices that are being used in a program should be allowed to generate interrupt request. This is an important point. The devices which are part of the currently executing program should be allowed to generate interrupt request. The devices which are not a part of the currently executing program are not able to generate interrupt request. Okay, so in order to control the device interrupt request from various devices, we use different bits of information and are given here in this diagram. Okay, the processor, here we have processor, keyboard and display unit, and these I/O interfaces associated with two registers, status register and control register. Status register consists of certain bit of information: DIRQ, KIRQ, SOUT and SIN. DIRQ means display interrupt request, KIRQ keyboard interrupt request, SOUT indicates that the display unit is ready to get new value from the processor for displaying. SIN indicate that whenever the keyboard is loaded with new value in order to pass that value to processor. And DEN, KEN. DEN means display enabled bit, KEN means keyboard enabled bit. The value of these bit of control register are very important, and the value of these bit of information is used to decide whether the device is allowed to generate interrupt or not. Why? That means the devices which are part of currently executing program whose enabled bit value become 1. The devices which are not a part of the currently executing program whose value of this enabled bit become 0. Consider a situation in which processor is executing a particular program in which we need certain input value from keyboard, and also the program does not generate any resultant values that want to be displayed through a display unit. What's the meaning? That means the currently associating with the currently executing program, we want to use the keyboard, and its display unit is not a part of the currently executing program, so that this information is represented using this bit of information. In our example, KEN value equal to 1 and DEN value equal to 0. What is the meaning? KEN value equal to 1 means this keyboard is associated with or used by the currently executing program, and this DEN equal to 0 means display unit is not going to use by the currently executing program. Okay, and whenever a user or a programmer pass some input value through the keyboard and is loaded into the data in register of the keyboard, then it automatically set this SIN bit value equal to 1. Okay, whenever this SIN value equal to 1, the keyboard want to inform the processor that data in register is loaded with new value, so that it generate an interrupt request. So before starting to generate or before generating an interrupt request, here we want to check the value of KEN bit. Here KEN bit equal to 1. That means this value 1 indicates that keyboard is a part of currently executing program, so that the keyboard can directly place an interrupt request. If this KEN value equal to 0, now in such situation, what's the meaning? This keyboard is not a part of the currently executing program. In such situation, if data in is loaded with new value, keyboard can't place any interrupt request. But in our example, KEN value equal to 1, and whenever this data in is loaded with new value, then automatically set this SN equal to 1. When SN equal to 1, the keyboard check the we want to check the KEN value. If KEN is also 1, then keyboard want to generate an interrupt request. Keyboard can generate an interrupt request. After placing an interrupt request, set this KIRQ value equal to 1. This indicates that keyboard is already generated an interrupt request. Okay. And also, after completing all the display activities, now the display unit is ready to display new value so that it can generate an interrupt request. So before generating an interrupt request, the display unit want to check the value of the DEN. Here it is 0. That means this display is not a part of the currently executing program. So that it don't want this display unit is not allowed to generate an interrupt request whenever this data out register become full of data out register is empty. Okay, so always remember the point. The devices which are now part of the currently executing program is allowed to generate interrupt request next. Okay, the devices which are the part of currently executing program are allowed to generate interrupt request, and the devices which are not a part of the currently executing program are always blocked to generate interrupt request. And this activity is based on the value of this enabled bit of information associated with the controller register. Okay, these all informations are about interrupt mechanism. Okay, in order to synchronize the data transfer between processor and IO devices. Okay, study well and thank you.